Let's do a quick recap. We had defined a problem called SAT. Okay, the input for SAT was clauses C1, C2, so on up to Cm. Each clause was an OR of literals, so it could be something like xi1 or xi2 or so on up to ik. Okay. So we had clauses C1 through Cm. Each clause was of this form, and the formula we consider is we think of the formula as C1 and C2 and C3 and so on up to and Cm. Okay, and the question we ask is this formula satisfiable? Okay, in other words, is there an assignment of values true or false to the variables such that the formula evaluates to true? Okay, so this is the question. So let me just go over this again. You have clauses C1, C2 and Cm. The formula we are interested in is C1 and C2 and C3 and so on up to Cm. Okay, each of these Ci's looks like this. Okay, these are you have xi1, xi2 and so on up to xik. You could have negations also. Okay, for instance, you could have xi1 or xi2 bar and so on. Okay, so each clause is an OR of literals, and the formula is an AND of clauses. Okay, and the question you ask is this formula satisfiable? In other words, is there an assignment of values true or false to each variable such that when you evaluate this formula, the formula evaluates to true? Okay, which means in each clause, when I look at each clause, there must be some literal which should evaluate to true. Either there should be an x and x should be set to true, or there should be an x bar where x is set to false. Okay, if x is set to false, x bar is true. So in each clause there must be at least one literal which evaluates to true. Then we say the formula evaluates to true, and such an assignment to these variables that gives you the value true is called a satisfying assignment. So the question we ask given a formula is, does this formula have a satisfying assignment? The formulae of which are of this kind, where you have an AND of clauses where each clause is an OR of literals, these formulas are called formulas in CNF, conjunctive normal form. Okay, all this we saw last time. So this is the problem SAT, and we also had a theorem. Okay, so this theorem is due to Cook, and it's called Cook's theorem, which states that if there is a polynomial time algorithm for SAT, then there is one for every problem in NP. Okay, so if there exists a polynomial time algorithm for SAT, there is one for all problems in NP. So in other words, satisfiability, this problem SAT, is among the hardest problems in NP. If you can solve this efficiently, if there is an efficient algorithm to solve SAT, there is one for every other problem in NP. Okay. So this somehow identified one a problem which is among the hardest problems in SAT. In fact, there is a name for these problems. So we call these problems NP hard. So these are hard problems in NP. Okay. So let me define this. So a problem is called NP hard if it has the following property. Okay. If it has the above property, which means if, what is the property? The property is this, if there exists a polynomial time algorithm for this problem, there is one for every problem in it. Okay. So the property we are looking for is this: if it has a polynomial time algorithm, okay, then there is one for every problem in NP. Okay, to be I guess more correct, I should say that if there is a polynomial time algorithm that solves this problem, then there is one for every problem in NP. Okay, so these are among the hardest problems, and hence they are called NP hard. There's one more definition I need, which is this: a problem is called NP complete. So a problem is NP complete if, okay, it has to satisfy two things. So let's say this problem is pi. Pi must belong to NP, and pi is NP hard. Okay, then it's called NP complete. Okay, so apart from being among the hardest problems in NP, I mean, it should be, see, when you say a problem is NP hard, okay, we do not require the problem to be in NP. The problem could be outside NP. Okay, as long as it has the property that if you can solve this problem, you can solve everything else in NP, it's called NP hard. But for NP complete, we require the problem to be in NP. Okay, the problem should be in NP, and it should also be NP hard. Okay, so that's the only difference. Okay, so now we can state Cook's theorem in a different way. Okay, so the theorem due to Cook, it states that SAT is NP complete. Okay, we saw that SAT was in NP. Okay, that SAT belonged to NP, and Cook's theorem essentially says it's also NP hard, which means putting these two things together, we know that SAT is NP complete. Okay. Essentially, NP complete problems are, just to state it again, they are among the hardest problems in NP. Okay, they have to be in NP, and they are among the hardest problems. Okay. So our goal is to add many problems to this set. Okay. To this set of NP complete problems, and we'll begin with clique, which also we defined last time. So let me just define problem clique. Okay, so problem clique is as follows. The input is a graph G and a positive integer k. Okay, and the question we ask is this: does G have a clique of size k? Okay, so this is the this is clique. We saw last time that This problem is in NP. Okay, there was a proof that the prover could give the verifier, so that the verifier, by looking at this proof and the input, could check that a given graph in fact did have a clique of size k. Okay. Our objective now is to prove the other part, which is that clique is NP hard, which means if there is a polynomial time algorithm to solve clique, there is one to solve everything else in NP. Okay. Again, we saw, I think I sort of hinted how we do this, and this is how we do it. Okay. So what we do is this: we have to use Cook's theorem to do this. Okay. So we show the following: if there is a polynomial time algorithm for clique, we'll show that this implies if there is, then there is one for, okay, so let me remove this if. So there is a polynomial time algorithm for clique will imply that there is a polynomial time algorithm for SAT. So this is what we'll prove. Okay, there is a polynomial, given there is a polynomial time algorithm for clique, we'll show that we'll construct a polynomial time algorithm for SAT. Now Cook's theorem says that if there is a polynomial time algorithm for SAT, there is one for everything in NP, and we'll use this. So just following these two implications, we can see that we proved what we want. Okay, so all that remains now is, I'll assume that there is a polynomial time algorithm for clique, and I'll construct one for SAT. Okay, so here's how we do it. Okay, so we have an algorithm for clique. So this is given. So we are given an algorithm for clique. Okay. Now what does this take as input? It takes as input a graph G, it takes k, and it says yes if the graph has a clique of size k, and it says no otherwise, right? Now what we want is this: we want a black box which will take, so this is, we want an algorithm for SAT, right? So the input to SAT is a collection of clauses, so C1 and C2 Cm. Okay, now we want to know whether it's satisfiable or not, yes or no. Okay, now what do these two answers? So somehow we have to use this subroutine. Okay, we have to use this as a subroutine to solve this problem. Now here is an example where the two things actually look quite different, right? This is a problem on it's something to do with logic. You have all these variables and you have clauses. This is a problem on graphs. Okay, so this is available in a subroutine, and we want to construct something. So how do we sort of use something, a subroutine which runs on graphs, to construct, to determine whether a formula is satisfiable or not? Okay, so here's the trick. So what we do is this: so we take these clauses. Okay, so we'll take C1 through Cm. Okay, so take C1 Cm. Now somehow I'll tell you how you construct a graph and some k. Okay, feed this, so feed into, so let's call this algorithm clique, into clique. Okay, and if this says yes, we'll say that the formula is satisfiable. Okay, if this says no, we'll say not satisfiable. Okay, so let's look at this. We take these formula C1 through Cm, we construct some graph G and some k, we feed this into this subroutine clique. Now this will say yes or no. If it says yes, we'll want to say that the formula is satisfiable. If this says no, then we'll say no. Okay, now Yeah. So how do we do this transformation? From these clauses, we have to construct a graph, right? And from a clique, what we get as output is whether a graph has a clique of size k. Somehow, a clique of size k should indicate that the formula is satisfiable. Okay. So let's see how this is done. Okay, so you take the formula C1 through Cm, and here's how you construct the graph. Okay, so for here are the clauses C1, C2, so on the way up to Cm. Now for each clause, I'll have a number of vertices in the graph. Okay, so let's say C1, x5. I'll tell you what these x5s are. X7 bar, C1, xt bar. Okay, if the clause C1 were x5, x7 bar, x5 or x7 bar or up to or xt bar, then I have a vertex for each of them. So in other words, I have a vertex for each literal clause literal pair. So if a literal appears in a clause, I have a vertex for that. Okay. Similarly, I have a list of them for C2. Okay, and so on. So Cm will have its own set of vertices. Okay, so for each clause literal pair, I have a vertex. I have divided the vertex set into these m parts, so one per clause. Okay, now what do we want is that from a clique of size k, we still haven't specified what k is. From a clique of size k, I should be able to figure out that there is a satisfying assignment. Okay, so what does a satisfying assignment look like? A satisfying assignment essentially says for each clause, which of them I can set to true. Okay, which literal I could set to true. Maybe I can set x7 bar to true, which means x7 to false. So maybe here I have, let's say, C2 and x13, x30. Maybe x30 I can set to true. Okay. Somewhere down the line, let's say C45, I have x30 bar. Okay, I could have x30 here and x30 bar elsewhere and so on. Okay, now somehow in each of these clauses, I want to set one of them to be true. I want to make that one of them is true. And this I should be able to pick out with a clique. So it stands to reason that I would like to have a clique of size m. Okay, and this clique I should pick by picking one vertex from each of these sets. Okay, I should be able to pick one vertex from each of these sets. If I'm picking only one vertex from each of these sets, then each of these sets better be an independent set. Okay, I don't want edges between any of these. All the edges in the graph may only go between vertices in different cliques. Good. Now, let's look at these two, C230 and C45, x30 bar. Now, clearly, I cannot, if I set this to true, I cannot set this to true. This will immediately become false. Okay, which means I should not be able to pick these two in my clique. Remember, the way we are going to get from a clique to a satisfying assignment is when I pick the vertices in the clique, they will decide which literal in a clause is satisfied, right? So this is roughly the intuition that I want. So from each vertex in the clique, I'll pick one vertex from a clause, and it will tell me which is the literal which is satisfied. So if I pick x30 in clique 2, I cannot pick x30 bar in clique 30 or 37. Okay, so these two I should not be able to pick, which means there should not be an edge between them. Otherwise, I can add all the edges. Okay, so this roughly actually is the construction. So let me formally tell you what the construction is. Construction of the graph is. Okay, so the vertex set. So the vertex set V is consists of C and L, where literal Okay, let me make this Ci and L. Literal L belongs to clause Ci. Okay, so there is one for each clause literal pair if the literal belongs to that clause. So what are the edges? So this is the vertices. Edge set is Ci x, okay, and it's a Cj y is an edge if and only if, first of all, I is not equal to j, because edges go only between vertices corresponding to different clauses, and x is not y bar, because if x is equal to y bar, okay, then I cannot pick both of them in my clique. So I can pick both of them in the clique if they are different variables altogether. Okay, one is x15, another is x30. It doesn't matter what value I set to each, right? But I cannot pick x and x bar together. Okay, so this is the graph, and k is n. Okay, so given my clauses, set of clauses, I construct this instance of clique. I feed it into the subroutine for clique. If it says yes, it has a clique of size m, then I say yes, the formula is satisfiable. It says no, I say no, the formula is not satisfiable. Okay, so let's actually formally prove this. Okay, so if we have actually informally argued this, but let's quickly sort of do a recap. Okay, so supposing the formula is satisfiable, so if formula is satisfiable, what does this mean? In each clause, so look at any satisfying assignment. Okay, if it's satisfying, there is a satisfying assignment, look at any satisfying assignment. In each clause, some literal will be true. Okay, so pick all this, so pick these vertices in the clique. Okay, so we have picked m vertices. Okay, we have picked one vertex per clause, so those are m vertices, and clearly there will be an edge between any two of them. Okay, because firstly they are in different clauses, and either they are the if they are the same sort of they use the same variable, then they cannot be negations of each other. Okay, so these in fact form a clique in the graph, and in fact the other sort of other direction is also similar. So take a clique of size m, which means there exists one vertex per clause. So I want to set these literals to true. Okay, so these literals which correspond to these vertices, set them to true, and you can check that this will be a satisfying assignment. In this clique, if a variable x appears, x bar will not appear, right? So this will be a satisfying assignment for the for SAT. Okay, we have just proved that clique is NP hard. We saw last time that clique is in NP, right? So put these two things together, we've just shown that clique is NP complete. Okay, so the thing to notice is that once we have Cook's theorem in hand, it's much easier to prove some other problem is NP complete. Okay, all you need to do is prove that if there is a polynomial time algorithm for this new problem, there is one for any of the old problems which you have already proved NP complete, for instance SAT. But now we can use cliqued also, right? Okay, so our next problem is called independent set. So let's define what an independent set is. So given a graph G, okay, V is the vertex set, E is the edge set, a subset U of V is called an independent set if there are no edges between any pair of vertices in U. Okay, if for all U1, U2 belonging to U, U1, U2 is not an edge. Okay, there are subset of the vertex set, so that if I take any two of them, there should not be an edge between them. Okay, this, I mean, for clique you wanted an edge between every pair. Here you do not want an edge between any pair. Okay, so our next objective is to prove a version of independent set, a decision version of the independent set problem to be NP-complete. Okay. Okay, what the search version of an independent set essentially states that given a graph, find an independent set of maximum size. The decision, so we convert this to a decision version in a fashion which is very similar to clique. Okay, so it looks like this. So independent set, problem independent set as input graph G and the positive integer k. Okay, the question you ask is, does G have an independent set of size k? Okay, this is the question we ask. Okay, so the first thing to see is this problem in NP. Well, I hope most of you can now show that this problem is in NP. Okay, anyway, let's do it. So if the answer to the question is yes, so we are looking at only yes inputs for which the answer is yes, and for these inputs the prover should be able to convince the verifier that in fact it is a yes input. Okay, so we need to figure out what it is that what is the hint or proof or advice that the prover gives the verifier. Okay, in this case again it's just the independent set. Okay, he just picks out k vertices from the graph and tells the verifier, here these vertices form the independent set. The verifier looks at these vertices, he checks that there is no edge between any of them. Okay, so that's what he verifies, and that's very easy to verify, and he can be convinced that in fact it is a yes input. Okay. The advice that the prover gives the verifier in almost all cases is, supposing the question is yes, why is this question yes? So you just answer that question. Okay, so here for instance, if it's yes, if G has an independent set of size k. Okay, so focus on the independent set of size k. If this is given to the verifier, then the verifier can check that it is in fact an independent set. Good, so this problem is in NP. Our job, or at least my job for the time being, is to prove that it's NP complete. So let's do it. Okay, so what we'll do is this. So we'll the strategy is so we want to show that independent set is NP hard. How do we do this? We'll do this. Okay, so assume there is a polynomial time algorithm for independent set. Okay, so assuming this, we'll construct a polynomial time algorithm for clique. Okay, what does this give us? Okay, we know that clique is NP complete, which means if there is a polynomial time algorithm for clique, there is one for everything in NP. Good, so that's what we'll use, and you can see that we are done if we can do this step, right? Assuming that there is a polynomial time algorithm for independent set, we construct a polynomial time algorithm for clique, and because there is one for clique, there is one for everything in NP. So we have proved essentially that if there is a polynomial time algorithm for independent set, there is one for everything in NP. Okay. This is not as difficult as the previous one. I mean, independent set and clique, they are both sort of problems on graphs, and they also look and feel similar, right? So in one case you have an edge, in the other, you have a subset where there are no edges. And in fact, this is exactly what we do. Okay, so supposing I have a polynomial time algorithm for independent set. Now, how do I find if a graph has a clique of size k? So I take this graph, okay, wherever there's an edge, if there's an edge between two vertices, I remove it. If there is no edge between two vertices, I add an edge. Okay, I sort of complement the edge set. And in this new graph, I feed into the independent set subroutine. If it says there's an independent set of size k, clearly these k vertices must form a clique in the original graph because I've complemented the graph, right? Well, this is all there is. So let's just write this down. So here's the transformation. So take G and K. So complement G to get GC. So what's the complement? Essentially the edge set is the same. Okay, I've complemented, the vertex set is the same and the edge set I've complemented. Okay, so the edge set of GC is, okay, so UV such that UV is not in E of G. Okay, if it's not there, I put it in. If it's there, I don't put it in. So this is a complement. So it's essentially a complement of EG. Okay, now feed this into. Okay, so feed this the subroutine for independent set. Okay, and if this says yes, then you output yes. If this says no, then you output no. Okay, so we recall that what we want is to find or decide if, okay, to decide if G has a clique of size k. This is what we are doing. Okay, we want to decide whether G has a clique of size k. We complement the graph, feed this into a subroutine for independent set, and if this independent set subroutine says yes, then we say yes. If it says no, we say the answer is no. And you can check that this works. I mean, in the sense that if G has a clique of size k, G complement also will have a clique of size k. If G does not have a clique of size k, if G has a clique of size k, then G complement will have an independent set of size k. If G does not have a clique of size k, then G complement will not have an independent set of size k. So the answer in both cases is correct. Okay, our next problem is it's called vertex cover. Okay, vertex cover. So what's a vertex cover? So a vertex cover in a graph G is a set of vertices such that every edge has at least one endpoint in this set, okay, is a set, let's say U of vertices, so that every edge has at least one endpoint in U. Okay, let's take an example. Well, okay, how about this? Okay, in this graph, let's see, suppose I pick this, then I pick this, okay, this, let's say that. Now, yeah, I need to cover this edge, so let's say that. Okay, now hopefully we have covered all edges. So this edge, this endpoint is in. For this edge, this endpoint is in. This edge, this is in. For this edge, this is in. Okay, for this both are in, but that's fine. Similarly, for this edge, both are in, and that's fine. And this edge, this is in. This is in the vertex cover. So if I pick these vertices which are tick marked, that forms a vertex cover in the graph. Okay, it's a subset of the vertex set, so that every edge has at least one endpoint. For instance, supposing you have a computer network, okay, you have a network and you want to monitor each link, right? You want to monitor each link. What you want to do is pick a set of these nodes, okay, pick a set of these computers, and to each computer you can assign a link, right? To each computer you can assign a link so that it monitors traffic on that link, both, I mean, going both ways, from the computer and coming into the computer. And you want a subset of the computers so that every link is covered, right? Which means for every link, at least one of the two endpoints must be chosen, okay, to monitor it. So this is the vertex cover. Ideally, you would like to pick a very small number of computers to do this job. And in fact, we will look for vertex covers of minimum size. Okay, given a graph, find the vertex cover of minimum size is the optimization or the search problem that one looks for. And our objective is to show that this is hard, this problem is hard, in the sense that if you can solve this problem, then you can solve every problem in NP in polynomial time. Okay, so this is among the hardest problems in NP. So if you want to pick a minimum number of computers to so that traffic on every link can be monitored, this problem is NP hard, and it's unlikely that you will come up with an efficient algorithm for this. Okay, so that's what we are going to do. Good. So I just mentioned the search version of vertex cover. What's the decision version? Remember, if you want to prove something is NP complete, okay, we look at the decision version. They are easier to handle, right? So here's how we do it. The trick is the same. We introduce this extra positive integer k, and we ask if the graph has a vertex cover of size k. Okay. So if it has a vertex cover of smaller size, clearly it has one of size k. Right? Okay. So here's the problem. So vertex cover, input is a graph G, and the positive integer k. The question is, does G have a vertex cover of sizes k? Okay. So I will leave it as an exercise for you to do, the following as an exercise for you to do, which is, supposing there is an algorithm for this problem, then argue that there is an algorithm for the problem of finding a minimum vertex cover. Okay, it's very similar to things we have done in the past. Okay, the other direction is simple. If you can find a vertex cover of small size, I mean smallest size, and clearly given this question you can determine whether there is a vertex cover of size k or not. If that size is smaller than or equal to k, or the vertex cover you found, then there is a vertex cover of size k. Okay, so adding vertices to a vertex cover, it still remains a vertex cover. So you can form as large a vertex cover, that's not a problem. In fact, if you put all the vertices in the vertex cover, if you take all the vertices in the graph, it will give you a vertex cover. Okay, that's what I want to say. Okay, so here's the problem, and we would like to prove that this is NP complete. The first thing we need to do is to prove that it is an NP. Okay, so the first step is VC belongs to NP. Now, why is this true? So what we do is, so we go to our usual game. So here's a prover, here's a verifier, okay, and here's the graph G and K. Now what does the prover give the verifier? Okay, the verifier is looking at this graph G and K. What does the prover give the verifier? So that the verifier can verify that there is a vertex cover of size K. Well, the prover just gives this subset of K vertices okay, so this is what the prover gives the verifier. Now the verifier looks at this subset, okay, and then he looks at every edge and checks that this, for every edge, one of the endpoints is in this subset. Okay, so that's what the verifier checks. He takes this subset of size K from the prover. Okay, now he goes through the edges one by one, and for each edge checks that at least one of these two endpoints is in this subset that the prover has given. Okay, so this proves that vertex cover is in NP. Now we need to show that vertex cover is NP hard. So we want to show that if there is a polynomial time algorithm for vertex cover, there is one for everything in NP, right? So we'll assume that there is a polynomial time algorithm for vertex cover. Okay, so what we'll do is we'll construct a polynomial time algorithm for independent set. Okay, instead of independent set, I could have chosen clique, or I could have chosen satisfiability, right? Either of these, one of these three problems I could have chosen. In fact, as we go along, we could choose any of these already proved NP complete problems here. But the trick is to choose the right one, so that if you choose the right sort of problem, then this proving this becomes easier. Okay, so we assume that there is a polynomial time algorithm for vertex cover. We'll construct a polynomial time algorithm for independent set. Okay, now how does one do this? Okay, what's the relationship between vertex cover and independent set? Okay, so here's my graph G, okay, and K. Okay, I have a graph G and K, and I want to find out if this graph G, does G have an independent set of size K. Okay, this is what we want to sort of prove, that we want to construct. Okay, this is the algorithm we want to construct, one for independent set. So supposing this is my graph G. Now supposing there is an independent set of size K, let's say this is the independent set. Okay, supposing this portion of the graph is an independent set. Let's look at what can we say? Okay, we know that there are no edges here, right? There are no edges between any pair of vertices here. Where are the edges in the graph? Well, the edge can be on this side, okay, or the edges can be of this form, right? Edges are either completely in this side, or one endpoint is here and one endpoint is there, which means that this portion is a vertex cover. Okay, if this portion is an independent set, this portion is a vertex cover, right? And in fact, this implication goes the other way. If this portion is a vertex cover, then the rest of the graph better be an independent set, because there cannot be an edge here, right? Every edge must have one endpoint in the vertex cover. So if a subset of the vertex set is an independent set, the complement of this set, this subset, okay, will be a vertex cover, and if it's a vertex cover, the other will be an independent set, right? So we'll use this to prove. So essentially, if you want to find independent set of size k, we will look for a vertex cover of size n minus k, where n is the number of vertices. So if there is a vertex cover of size n minus k, then clearly there is an independent set of size k, okay? And if there is no vertex cover of size n minus k, there is no independent set of size k either, right? So that's all there is. So what we do is we just take the same graph, instead of k we make n minus k, okay, and then we call the algorithm for vertex cover. So we are given an algorithm for vertex cover, we are constructing one for independent set, okay. So we take g and k. So we want to find we want to determine if G has an independent set of size k. Okay, what we do is we take G prime and k, where the vertex set of G prime is vertex set of G prime is the same as the vertex set of G. The edge set of G prime is also the same as the edge set of G. Okay, this should be k prime. K prime is nothing but n minus k, where n is the size of the vertex set. So this is the same graph as the original, okay. So you just copy the graph down, and k prime is nothing but n minus k. And now you ask if this pair, okay, for this pair I feed this into the subroutine for vertex cover. So you ask, so this is fed into subroutine for VC, okay. If it says yes, then you output yes. If it says no, then you output no. Okay, that's it. So G and K are input. Okay, this is an algorithm for independent set. Okay, G and K are input. I take the same graph and I take n minus k as k prime. Okay, G prime is the same as G and k prime is n minus k. This I feed into a subroutine for vertex cover, which we have assumed. Remember that we have assumed that there is a polynomial time algorithm for vertex cover, and if this says yes, okay, then our output is yes. If this says no, our output is no, okay. And it's easy to see, we have argued that if G has vertex cover of size n minus k, it has an independent set of size k, okay. And if it does not have a vertex cover of size n minus k, it does not have an independent set of size k, okay. So we've just added a new problem to our list of NP-complete problems. We've just proved that vertex cover is NP-complete, right. So we started out, Cook's theorem gave us SAT, right. SAT was NP-complete, and we then showed that clique is NP-complete. Then we showed independent set is NP-complete, and now we have showed that vertex cover is NP-complete, right. Okay, so our next problem is very similar to vertex cover, but it's a restricted form of vertex cover, okay. So this is called less than equal to 3 VC, okay. So the input is a graph G such that the maximum vertex degree is at most 3, okay, and a positive integer k. The question is the same, does G have a vertex cover of size k? Okay, without this, okay, if I omit this, just graph G and positive integer k, this is just vertex cover. Okay, I add this additional constraint to the input. The only inputs I can look for is graphs where the maximum vertex degree is 3. Delta of G is the maximum vertex degree in G. Okay, delta of G is max degree of a vertex in G. So look at the degrees of vertices in the graph, and delta is the maximum. So the maximum degree I want is 3. So this problem is like vertex cover. The only thing is that we focus on graphs, on only some graphs, okay, not all graphs, only graphs which have maximum vertex degree at most 3. Now, is this as hard? We know that vertex cover in general is a hard problem, right? Is this problem as hard? I mean, is it as hard? Is it much easier to find vertex covers in graphs where the maximum degree is just 3 and not, it can't be more than 3? The answer is no. In fact, even in this case, okay, the problem turns out to be hard. So even for graphs where the degree of a vertex doesn't exceed 3, vertex cover, problem vertex cover is hard. Okay, so we'll show that this version, this problem is NP hard or NP complete. To prove that this is an NP is very similar to the vertex cover thing, and I will not do it. Okay, so just do it. I hope most of you can do it. All of you can do it. Good. So we'll just prove that less than equal to 3 VC is NP hard. Okay. Now, which of the problems which have already been proved NP complete should we use for this? I guess vertex cover is the closest, so one should go for vertex cover, and it's correct. So vertex cover is what we will use. So what we'll do is, given an efficient algorithm or a polynomial time algorithm for less than equal to 3 VC, we would like to construct an efficient algorithm, polynomial time algorithm for VC, for general VC. Okay. So let me write the statement down. So given a polynomial time algorithm for less than equal to 3 VC, we want to prove that we want to construct a polynomial time algorithm for VC. This is what we want to do. And once we do this, we know that from the previous construction that there is one for everything in NP, right? So let me just sort of say what this means. See, going the other direction is easy. Supposing you have a polynomial time algorithm for VC, clearly if you restrict the input in any way, it doesn't sort of, you can still feed the same input to the algorithm. But here you just cannot do that. Okay, your input is a graph and k. Now this graph could have vertex degrees which are much higher than 3. What do we do with these? Okay, that's the crux. If all vertex degrees were 3, then there is no problem. I just feed this into the algorithm for less than equal to 3 VC and we are done. Okay. So what happens when there are vertices with degree greater than 3, 4, 5, 6, whatever, up to n minus 1? Okay, it can be as large as n minus 1. Well, the trick is to somehow start decreasing the vertex degrees by creating new. So given this original graph, I'll construct a new graph where the vertex degrees are smaller, and somehow you must have some control over the vertex cover. The vertex cover in the new graph must be related, very closely related to the vertex cover in the old graph. Okay. So here's the trick. So I'll tell you what the trick is to reduce the degree of a vertex. Okay. So the trick, main trick, TRICK, is degree reduction while keeping the size of the VC while controlling. So the size of the VC, if there is some control over how it changes, then we are through. Okay. So let's take. Okay. So here is a vertex, let's say of degree 5. Okay. Somehow I need to. Here is the rest of the graph. Okay. So what I do is this: to change the degree, I break it up into 3 parts. I break this vertex into 3 parts. Okay. So here is the rest of the graph. Okay, let's say 3 of them here and 2 of them here. Okay. So let's see what I have done. See there are 5 of them. I've just broken it up into 2 parts. Okay, let's say 1, 2, 3. This is A, B, C, D, and E. A, B, C. So this one vertex I have broken up into 3 vertices. Okay, I have added 2 new vertices. Okay, and you can see that vertex degrees are decreasing. Initially I had one of degree 5, and now if I look at these vertices, there is one of degree 2, there is one of 3, and one of degree 4. Okay, so this vertex degrees I have decreased. If this were 4, okay, I wouldn't have one of these edges. Let's say this to A was not there, then I am done. So I have 3 vertices, one of degree 2 and 2 of degree 3, and I am done. Right? I have decreased the vertex, the degree of a degree 4 vertex. If it's 5, I'll have one with 4. If I have larger, again I just split it into 2 parts. Okay. Of course, I have to do this repeatedly. I take this graph, I split this vertex into 2. Okay, I decrease the degree, and I keep doing this till every vertex has degree 3 or less. Okay, so that's the rough idea. Let's see what happens to the vertex cover when I do this split. So just to sort of recap, I look at this graph, look at if there is a vertex of high degree, I split this degree up. Okay, I split this vertex into 2 parts and add another vertex. Okay, so instead of a vertex, I now have 3 vertices, and the degree has reduced. Right, which initially were 4, now they have 2 of them are degree 3 and 1 has degree 2, and so on. So I keep doing this. Now I have to somehow say that the vertex cover doesn't change much. Even if it changes, I must say that it changes clearly by this much. Only then can I make a connection between the vertex cover in the final graph and the vertex cover in the original graph. Okay, final graph has degree of every vertex at most 3, that is fine. I should also be able to say that if there is a vertex cover of this size in the final graph, if and only if there is a vertex cover of size k in the original graph. Okay, and that we'll see right now. So supposing the claim is this, so here is the graph G and here is graph say G prime, which I get this way. Now the claim is that G has a vertex cover of size k if and only if G prime has a vertex cover of size k plus 1, which means the size of the minimum vertex cover goes up by 1. Okay, so this is my, each time I use this split, the vertex cover size goes up by 1, at most 1. Right? So why is this true? So let's prove both ways of this inequality. Okay, let's prove this. Supposing G has a VC of size k, why should G prime have a vertex VC of size k plus 1? So take the VC which G has. Okay, there are two cases. So case 1 is, let's call this vertex u. Okay, and here let me call these u1, u2, u3. Okay, case 1 is u belongs to the VC. Now if u is in the VC, then put u1 and u2 in. The rest of the vertices in the vertex cover remain the same. Okay, there are some of these vertices in the vertex cover in this portion of the graph, and I have u. I put u1, u2 and the same set of vertices here in the vertex cover. Okay, and now let's observe that this is also a vertex. So the vertex cover size has gone up by 1, right? If there were L plus 1 L vertices here and 1 vertex here, then I have L vertices here and 2 vertices, so it's L plus 1. Why is this a vertex cover? Now if the edge is completely in this portion, it is covered, right? Now since both u1 and u2 are in, these edges are covered and these two edges are also covered. So every edge is covered, right? So this is a vertex cover. Now case 2, u is not in the VC, then put u3 in the VC. Okay, so now again let's check that this is a vertex cover. Now all of these vertices, all of these edges AU, BU and so on have to be covered, which means A, B, C, D, E must be in the vertex cover, U is not in the vertex cover, right? So all these edges are covered by the vertex cover in this portion, since A, B, C, D, E is in the vertex cover. So the only edges we need to worry about is U1, U3 and U2, U3, and because we put U3 in the vertex cover, these two are also covered. So this is also okay. Okay, just to recap, if U is in the vertex cover, remove U from the vertex cover and put U1 and U2 to get the new vertex cover in G prime. Okay, this is a vertex cover. If U is not in the vertex cover, take the old vertex cover and put U3 additionally in this vertex cover, and this will be a vertex cover in this new graph. Okay. Okay, this proves one direction. So we need to prove the other direction, and which that's also very simple. Now just observe. So let's look at U1, U2 and U3. Okay. Now there are two cases again. So look at a vertex cover here. I will show that there is a vertex cover of size 1 less on this side. Okay, if there is whatever vertex cover is there on this side, I'll show there is one of size 1 less. So the case 1 is U3 belongs to the vertex cover. So remember, this vertex cover is in G prime. Okay. Then, well, I just remove U3, and you can check the rest of the vertices will form a vertex cover for this portion. Okay. Okay, I must say that only U3 is in VC, but not U1 and U2. So only U3 among U1, U2, U3. So that's case 1. Okay, U3 is in the vertex cover, but U1 and U2 are not in the vertex cover. Now that means that A, B, C, D, E, all of these edges are present in the vertex cover, right? So these edges are taken care of, and clearly if there's an edge only in this portion, it's taken care of here also, because this portion of the vertex cover remains the same. I have just removed U3, right? So if U3 is in the vertex cover, U1 and U2 are not in the vertex cover, then you are done. You just remove U3. Okay. So the next case, so case 2, if it is not this case, so let's look at U3, U1, U2. Then I claim that at least 2 of U1, U2, U3 must be Okay, two of these. So why two of these? Well, I can't have only u1 in the vertex cover. Okay. I cannot have only u1 in the vertex cover, because if both u2 and u3 are not there, then this edge is not covered, right? The case only u3 is taken care of. So we must have at least two of these. Okay. In this case, I remove this and put, so remove and put u in the VC instead. Okay, then I get vertex cover of 1 less. Well, what if all three are present? Well, this cannot be a minimum vertex. If there is a vertex cover of this size, there is one of smaller size on the right hand side. Okay. So that doesn't impede our progress. Good. So when I do the split, the vertex cover may rise by at most 1. Okay. The vertex cover, will rise by at most 1. Okay. Okay. So then the procedure is clear. I start with G and I do the sequence of these transformations. Okay, G1 and I get G2. Each time I split a vertex into 3, right? So I keep doing this as long as there is a vertex of degree 4 or greater. Okay, so finally let's say I end up with GL. Okay, I have done this L times and I get a graph. So delta of GL is less than or equal to 3. Okay. So I want to find out if G has a vertex cover of size k. Right. What I do is I ask if this has a vertex cover of size k plus L. If it says yes, I say yes, G has a vertex cover of size k. If it says no, I say G does not have a vertex cover of size k. Okay. And the proof that it works essentially is we have actually done it. The reason is each time we do a split, the vertex cover rises by 1. Okay. So this actually proves that less than or equal to 3 VC is NP complete. There is just one small thing that we need to worry about. Well, you start with an initial graph and you start splitting. What if there are just too many splits? Right? We want a polynomial time algorithm for this. We started out with a graph, and supposing in constructing this new graph we take a lot of time, then this will not work. Okay. We'll show next time that this is not true and L is bounded. Okay. So L will not be too large. If we show that L is not too large, then the final graph is not too big, and so our entire procedure will run in polynomial time.